Good morning. In this video, which is topic number 4, we are going to study three different antenna parameters. First, radiation intensity. Second, beam efficiency. And third, antenna directivity and gain. So let's begin with radiation intensity. Radiation intensity of an antenna is defined as power radiated from an antenna per unit solid angle. The concept of solid angle we have studied in detail in the previous video. So a sphere has a total solid angle of 4 pi steradians, which comes as 41,253 square degrees. So a sphere radiates power through the entire solid angle of 4 pi steradians. 4 pi steradians, and that is called as radiation intensity U. The unit, as the definition indicates, is watts per steradian or watts per square degrees. We normalize the power, which is function of theta and phi. It can be power or electric field. So the normalized power as a function of theta and phi can be represented in terms of radiation intensity U as U of theta comma phi divided by its maximum value, U of theta comma phi max. This can be also represented in terms of Poynting vector. Yes, because Poynting vector indicates power density per unit area. So the Poynting vector, yes, depending on the distance from the antenna, which inversely varies with the square of the distance. The next concept is beam efficiency. Do not confuse with another parameter known as antenna efficiency. Beam efficiency and antenna efficiency are totally different. In beam efficiency, we define the efficiency of the beam. As you know, in the radiation pattern of an antenna, there are major lobes and minor lobes. Side lobes and back lobes are termed as minor lobes, and major lobe is the lobe in which the intended radiation happens. If area of, now you have studied the concept of beam area. If we name area of each lobe type by indicating omega capital M for major lobe and omega small m for minor lobe, then efficiency can be defined by taking the ratio of omega capital M, which is beam area of major lobe, divided by total beam area, which is addition of beam area of major lobe and minor lobe. Similarly, if you take the ratio of beam area of minor lobe to the total area, minor lobe is the region in which the radiation pattern is not expected. So if we take this ratio, it cannot be efficiency, but it is defined as stray factor. You can see beam efficiency is a dimensionless number as it is a ratio of two identical quantities, and if we add the beam efficiency, which is indicated by epsilon capital M efficiency plus epsilon small m stray factor, if we add these together, the total is 1. The next concept is directivity and gain of an antenna. Directivity of an antenna is defined as ratio of the maximum power radiated by an antenna to its average value. So this maximum power radiated by an antenna can be 4 pi steradian in case of an isotropic radiator, and the average value of power radiated, that is equally in all direction what we say, that can also be 4 pi steradian in case of an isotropic radiator. Thus, the lowest possible value of directivity is 4 pi divided by 4 pi is equal to 1, and since this is a ratio of two identical quantities, the directivity is a dimensionless number. Now, as we know, all practical values radiate its maximum power over area less than 4 pi. Therefore, directivity value is always greater than 1 in case of practical antennas. Since I am writing, since it's equal to 1, I am writing here greater than or equal to, but in all practical cases, directivity is always greater than 1. Highest the directivity indicates that lowest the region or area through which the maximum power is radiated by the. This definition of directivity is known as directivity from patterns, because we are taking the values of maximum power and average power from patterns. Let's now find the second definition of directivity, that is from beam area. We have seen the beam area concept in the previous video. So let's now find out what is directivity in terms of beam area. And of course, we make use of these two equations. So let's first write what is equation for average power over a sphere, which is in the denominator of this equation. So the average power P of theta comma phi, let me tell you once again that we define the pattern in terms of power or field. If we are defining the pattern in terms of field, then we need to take the square of the field term in order to get the power. So let's define this equation in terms of power now. So average power is given by, over the surface of sphere is given by double integral of limit phi ranging from 0 to 2 pi and theta ranging from 0 to pi, the power radiated by an antenna as a function of theta comma phi into sine theta d theta d phi. You know that this term is the beam area d omega. We have studied this in the previous video. Now, since we are writing the equation for average power over a sphere, this term need to be divided by 4 pi. So it is 1 upon 4 pi. Why 4 pi? Because we are talking about average power over a sphere, and you know that a sphere subtends totally 4 pi steradians. So this is equation for this denominator term. Now let's simplify this equation and write it as 1 upon 4 pi integral over the surface of sphere P of theta comma phi, and this term sine theta d theta d phi is known as d omega, which is beam area subtended by an incremental region dA. You can refer my previous video to understand this d omega term. Therefore, after substitution of this term, average power term, in this equation, we get directivity is equal to P of theta comma phi max divided by 1 upon 4 pi integral over the surface of sphere P of theta comma phi d omega. We know that we represent a normalized power by defining the power radiated by an antenna by its maximum value. So let's first define this power radiated by an antenna in terms of normalized value. So the equation becomes P of theta comma phi max divided by 1 upon 4 pi integral over the surface of sphere P of theta comma phi divided by P of theta comma phi max. By dividing the power radiated by an antenna by its maximum value, we are actually obtaining the normalized power into d omega. So this whole term here will become Pn of theta comma phi. So let me write this equation here, which is actually equal to d P of theta comma phi max divided by 1 upon 4 pi integral over the surface of sphere Pn of theta comma phi into d omega. Now if you remember from my previous video, this term inside this rectangle is nothing but omega a. So when we have defined this term p of theta comma phi divided by p of theta comma phi max, we have divided by p of theta comma phi max in the numerator also. So it is p of theta comma phi max divided by p of theta comma phi max. I missed this step in the previous explanation. So these two terms get cancelled. So actually here in this equation, in the numerator, we don't get this term, we get 1. So the directivity equation is now 1 upon 4 pi integral over the surface of sphere 4 pi normalized power of theta comma phi d omega, and this whole term is, as I mentioned earlier, omega a. So the equation now becomes, directivity equation now becomes d is equal to 1 upon 4 pi omega a, which is equal to, if this 4 pi goes in the numerator, it is 4 pi upon omega a. So this equation of directivity is in terms of beam area. You can see here the directivity is defined as ratio of two beam areas. Now you may surprise why this 4 pi is beam area. If you remember from previous video or previous lecture, 4 pi is beam area subtended by a sphere divided by omega a, which is a beam area subtended by any practical antenna. Now in the very first case, suppose if we assume that the denominator term omega a is the beam area subtended by a sphere again, then the directivity will become, as I mentioned earlier, 4 pi divided by 4 pi is equal to 1. If we take some practical antenna's case and it is radiating, let's say in case 1 the antenna is radiating over the surface of sphere. In the second case, in practical case, let's say we are taking the example where the antenna is radiating only over the half sphere. Then in the second case, the omega a value will become half of 4 pi, which is 2 pi. And in that case, the directivity will become 4 pi divided by omega a is 2 pi, which is equal to 2. So you can see the difference and the dependence of beam area on directivity. Directivity becomes double the moment beam area becomes half. The next concept is gain of an antenna. The gain of an antenna is an actual or realizable quantity which is less than directivity because it is product of directivity into efficiency. So this is another term I was mentioning in this video, that is antenna efficiency. It is not beam efficiency, but it is the overall efficiency of an antenna, and it depends on ohmic losses and radiation losses. Because an antenna is a metallic structure, there are losses related to ohmic conditions, and there is also loss related to the reflection, which is called as a radiation loss. So if we take into consideration the losses, the efficiency that we get multiplied by directivity is called gain. So this equation can also be put in words like this. Gain of an antenna is defined as how efficient an antenna is in the given direction. So efficiency is always somewhere between 0 to 1, which is 0 to 100%. And in case of laboratory antennas, the procedure to find out the gain is this formula, where we have a particular antenna under test. We find out the maximum power radiated by the antenna under test, and we take the maximum power radiated by a reference antenna whose power is known, and we multiply it by the gain of the reference antenna which is known. So using this formula we compute the gain, or else we have a formula where we multiply the efficiency of an antenna for a given directivity and compute the gain. There is a procedure to find out approximate directivity using half power beamwidths. So a directivity can be computed by considering the beam area in square degrees for a sphere, which is 41,253 square degrees, divided by theta in the half power direction and phi in the half power direction, the product of theta and phi. So in the next video, we will see numericals on computing approximate directivity using this formula and finding the gain based on the efficiency given and the directivity computed.